Hello everyone, welcome to lecture 35 of the online course Modern Display Technologies Flat Panel Display. Today's lecture is on bistable cholesteric reflective displays and drive scheme. So this is basically the part 2 of the lecture. So part 1 was in lecture 34. So here is the lecture outline. We'll have a brief recap of the part 1. We'll talk about the planar focal conic transition mechanisms. Here we'll be focusing on the new ones as well, the fingerprint homeotropic transition that leads to unwinding the helix. Homeotropic to planar transition, there are two relaxation modes, okay, and then the bistable cholesteric voltage pulse response curve. We'll then talk about the conventional and dynamic drive scheme for passive matrix addressing, and we'll talk about the applications of bistable cholesteric displays, and finally provide a summary to this discussion. So the part 1 basically established the 4 cholesteric structures, the optics of the planar, that is the reflective state, and the multi-domain origin of grayscale. Part 1 finished with the discussion of the energy balance driving the planar to focal conic transition. That was like the zero elastic electric energy for the planar, and then you have positive elastic but negative electric energy for the focal conic. That is why little bit of application of electric field was able to drive that transition, right? So today's lecture builds directly and continuously on it, okay? So today the detailed mechanism of all 3 key transitions. We'll discuss about the material's full voltage pulse response and the true practical drive schemes which are basically built on top of that response. So let us focus on the planar focal conic transition first. There are basically 2 mechanisms, okay. So let us distinguish the 2 mechanisms carefully. Oily streaks, okay. So these are the bent layer defects that nucleate from impurities above a threshold, that is EOLE, and then grow until the whole cell transforms, okay. So figure 1 basically shows, here you can see the microphotograph of the oily streak defect in a cholesteric liquid crystal, okay. So the bright finger that is seen here, that is the oily streak, and the dark background is basically the planar texture, okay. Here you can see the structure of the oily streak on the cross section. So what you understand, that the oily streaks require nucleation from a defect or impurity site, and then it basically grows with time. So it's an inhomogeneous seeded process. Now you see the second mechanism, which is basically Helfrich deformation. This is basically a 2D undulation of the cholesteric layer which can regulate homogeneously above a threshold called E. Helfrich. So this is the microphotograph of the Helfrich undulation deformation structure. So here you see the deformation that is shown in a plane perpendicular to the cell structure, you can see here. So what you see here is that the difference. So you can clearly understand that the Helfrich deformation is homogeneous, it's not seeded, so it proceeds much faster than the oily streak pathway, and the wavelength of the undulation is given as lambda, which is basically 2k33 by k22 divided to the power 1 by 4 into h into p naught square root, okay. So that's basically to the power half, okay. So what is p naught here? P naught is the intrinsic zero field pitch, fine. So the design goal here is to keep the planar to focal conic threshold high, so addressing column voltages don't cause unwanted flicker, okay. So this is just as those SSFLC and the BTN, they needed their crosstalk avoidance conditions, okay. So here you basically also want bistable cholesteric drive schemes require this planar states switching threshold comfortably above the voltages seen by the non-addressed pixels to avoid unwanted flicker, right. Now if you look into the fingerprint to homeotropic transition, okay, so here what happens, as the field increases from focal conic, the material basically gradually shifts from its fingerprint texture, where you see helical axis parallel to the surface. As the field actually increases from the focal conic, you will see the material gradually shifting towards the fingerprint texture, where the helical axis is parallel to the surface. So this is where you have E equals 0, and then this is what happens when you have E greater than EC, okay. So you will see in the fingerprint texture no sharp boundary between the two, okay. Now when the field increases further, the fingerprint pitch itself grows longer and the helix is gradually being unwound, okay. So the critical field that is unwinding the helical structure is given as EC, okay. So E greater than EC, the unwinding happens here. So EC is basically pi square divided by P naught times K22 divided by epsilon naught delta epsilon to the power half, okay. So P naught is nothing but the intrinsic zero field pitch, K22 is the twist elastic constant, and epsilon naught delta epsilon is basically the dielectric anisotropic term. Now what you see here above a critical field EC, this unwinding field, okay, here you see the pitch becomes effectively infinite. That means your helical structure is fully unwound and the material has basically reached a homeotropic state. Now the reverse, that is homeotropic to fingerprint transition, is a very slow, or comparatively you can say it's a slower nucleation process with hysteresis. It restarts only below a threshold called EHF, okay, and that is experimentally found to be around 0.9 times of EC, okay. So here we will discuss the homeotropic to planar transition and the two relaxation modes which are there, okay. So when the field is reduced from homeotropic, two different relaxation modes are possible depending on how the field is dropping, okay. So this is the relaxation from the homeotropic state to the planar state, this is the timeline, okay. So this is the homeotropic state. Now if the field stays between EHP and EHF, so what happens, the liquid crystal relaxes slowly via nucleation into the fingerprint state and then to the focal conic state, okay. So that is basically the HF mode from the previous slide. Now if the field drops below EHP, okay, that is the normalized critical field. So in that case what will happen, the liquid crystal instead can relaxes quickly to the planar or you can say it's a transient planar state, where the pitch is temporarily stretched to about twice the intrinsic value, and then over say some time, say 100 millisecond, it settles to a true stable planar state, okay. So these are the different pathways which are being discussed. So these are basically the free energy of the conic helical structure, which is shown as a function of the polar angle theta at various applied fields, okay. So this homeotropic to planar relaxation is the pathway that a bistable cholesteric drive scheme deliberately triggers to write the reflective, that is the bright state. Now the unnormalized critical field for this planar homeotropic transition, that is this EHP, okay, is 2 pi into square root of K22 by K33 into EC. So here we'll see how this bistable cholesteric basically responds to a voltage pulse. Now let us consider the material starting in the planar state, that is in the curve A, and this is the voltage scale and this is the reflectance that you are seeing, okay, and then you apply a voltage pulse of a given amplitude here, okay. So below a stability threshold voltage V1, okay, this is the stability voltage level, nothing changes and you will see that the material basically stays fully planar. Now what happens between V1 and V2, these two voltage level? So you are basically from V1 you are increasing the voltage level and you are seeing that the reflection is basically dropping. That means the state is basically getting progressively transferred, or you can say more domains are now converting into focal conic, and that is why the reflectance falls smoothly, and this particular thing is useful grayscale window. Now what happens at V2? Above V2 you will see that each domain has basically already switched to focal conic, where the reflectance has already reached its minimum, and that is basically the dark state, because this is the lowest level of reflectance. So you can basically mark this V1 as the onset of switching, and V2 basically marks the completion of this planar to focal conic transition. Now the important idea here is that the cholesteric liquid crystal does not switch abruptly. There is this domain by domain transition happening between this V1 and V2 voltage level that enables this analog or the grayscale control. Now if you continue on this graph, what you see here is that above V3 some domain again starts switching to homeotropic, okay, which basically relax back to the planar after the pulse. So after V3 you will again see that the reflection basically starts rising. Now above V5 what happens? Every domain basically reaches homeotropic during the pulse and all of them basically relax to planar. So your maximum reflectance level of the planar state is again basically restored, okay. Now let us say that you are basically with this curve, that is the one with the circles, follow this bottom curve here, okay, that is basically the focal conic state, okay. So if you are basically starting from this curve, the reflectance stays low until V4, okay. So only after V4 you will see that in the focal conic state the transmission is the dominant one, so reflectance is low, but only after V4 you will see the domains begin switching through homeotropic and then finally to the planar state, and that is why it is going to approach there. So by V6 you will see that the focal conic sample is also completely converted to high reflectance planar state. However, these different thresholds that you see here, V3 and V5, in the other case, in the focal conic case, you are basically seeing V4 and V6. That shows that the response basically depends on the initial liquid crystal state, and this is what is the signature of bistability or hysteresis. So what is the main takeaway here is that the reflectance voltage response is non-monotonic. First it is decreasing, then increasing, and this behavior is basically exploited in the cholesteric liquid crystal driving scheme. So let us see how the conventional drive scheme looks like. Okay, so in a conventional cholesteric liquid crystal drive scheme, pixels are addressed one row at a time using row and column voltages together. Okay, a high voltage pulse basically selects the reflecting planar state, and a low voltage pulse basically selects the non-reflecting focal conic state. Okay. Now the selected row, so this is the diagram that shows the row and the column voltage assignment for the conventional cholesteric driving scheme. So here you see this row not being addressed, this row has got a voltage pulse, so this is being addressed, and these two are also not being addressed. Here what is happening, here different pulses are applied to different columns. So what is happening is that the addressed row voltage is basically VA, that is V6 plus V3 by 2. Okay, so this is such that the column voltage can shift the final pixel voltage toward either switching condition. Okay, so if you put the column voltage to be minus delta V by 2, that will basically select planar, and if you take the column voltage to be plus V by 2, that will basically select focal conic. Okay, so what is delta V? That is basically the difference between V6 and V3. Now combining this row and column voltages, that basically give you either V6 or V3 across all the selected pixels, right? Now if V6 is basically used to obtain the planar, so wherever you are getting V6 you are getting planar, and if you are getting V3, that is used basically to obtain the focal conic, that means the low reflectance of the dark state. Okay, that is like here. So the row voltage here is VA, that is V6 plus V3 by 2. Okay, and the selecting planar state, you are applying minus half delta V. So delta V is basically V6 minus V3. Okay, so when you combine this and the row voltage, you are basically getting V3, which is basically the focal conic. Okay, so this is basically a matrix diagram which shows these 4 columns with different combination of P, that stands for planar, and FC basically stands for focal conic pixels, which are driven by the assignment of the voltages, okay, which are shown. So the row voltage basically selects which row is being written, while the column voltage basically determines whether that particular pixel will become a P or a FC. Now the rows that are not being addressed receive a non-addressing bias VNA. Okay, this one. Now keeping their effective voltage away from the threshold, switching thresholds. So what is the main idea here is that the row column voltage superposition will allow individual pixels to be written without disturbing the previously stored pixel, and that is very important for passive matrix bistable cholesteric liquid crystal displays. Now what you see here is that in this particular non-conventional drive schemes, non-addressed rows basically sit at 0 volt, and the resulting pixel column voltage swing is basically plus minus half delta V. So if you take a numeric example, okay, that was discussed in the lecture 32's SSFLC analysis, or even in lecture 33's BTN analysis, there we will see that the non-addressed rows will see column voltage swing of plus minus half delta V, that turns out to be plus minus 7 volt. Okay, and that is safely beyond the stability threshold voltage of V1, that is typically 18 volts. Okay, so as I mentioned, this stays safely below the stability threshold voltage V1 of 18 volts. So non-addressed pixel states are basically undisturbed, and the crosstalk prevention condition is basically satisfied. So limitation of this technique is that addressing one line takes a few tenths of milliseconds, so it makes it workable only for low information content displays, echoing that the same speed bottleneck was also seen in the BTN's one phase scheme, right? So both conventional schemes are basically limited by needing to complete the full relaxation process for each line before moving to the next line. So this basically motivates anyone to go for the dynamic drive scheme, which basically restructures the waveform to pipeline the slow parts. Exactly the same general trick that was used for BTN. So what you can do, you can separate the waveform into phases so that only the shortest state determining phase must be sequenced line by line. Okay, so here is how this particular scheme looks like, the dynamic drive scheme. Okay, so here we'll see that the dynamic drive scheme basically uses 3 stages, or you can say 3 phases per line. Okay, so that directly exploits the homeotropic relaxation mode split from the earlier one. So the 3 phases are basically preparation, selection and evolution. So what happens in the preparation phase that lasts for around 50 milliseconds? Here a voltage Vp basically switches the liquid crystal fully to homeotropic state. Okay, this effectively resets the liquid crystal before writing. Then comes the selection phase, which is for around 1 millisecond. So here the applied voltage determines which relaxation path the liquid crystal will follow. If your VH is greater than VHP, okay, so in that case the liquid crystal is kept in the homeotropic state during the selection. If you consider VL less than VHP, okay, in that case the liquid crystal immediately starts relaxing through the transient planar state. Okay, and then comes the evolution phase, which follows immediately after that. So here these 2 different starting conditions will develop into different final textures, either of planar or focal conic. So the final optical state is basically determined mainly by this very short selection phase rather than by applying a long writing pulse. Okay, so here also you can see this is the selecting of the planar state. So for homeotropic, you are staying in homeotropic till homeotropic, and then you are in the planar state. For selecting the focal conic, you are basically doing it like this, that if your VL is less than VHP, in that case the liquid crystal immediately starts relaxing to the transient planar state. Okay, and then you actually land up in the focal conic state. Now you can also see that the evolution state phase, you will say the evolution phase is also around 50 millisecond. Here the applied voltage V basically let us choose the chosen relaxation pathway to complete. So if it will take you to planar if VH was selected, or it will take you to focal conic if VL was selected. So if you consider the VH path, it stays homeotropic through evolution, since your VE is actually above the VHF voltage. Okay, so it can basically relaxes fully to the bright planar state. So once the evolution ends and the voltage drops to 0. If you consider the VL path, there the transient planar state comes in between, that is the unstable phase under the evolution phase field, that is carried on to a dark focal conic state by the end of the evolution. So with preparation and evolution pipelined across many lines, the frame time can be obtained as T frame equals delta Tp plus n, where n is the number of rows, into delta Ts plus delta Te. Okay, so this is the selection, this is the evolution, and this is the preparation time. Now an important advantage here is that Relatively long preparation time can overlap or pipeline across different rows, and only short selection intervals needs to be performed row by row. Okay? Therefore, compared to the conventional drive scheme, the dynamic method can provide much faster addressing of a bistable cholesteric liquid crystal. Okay. Now look at this equation, you can also understand that the frame time is fast enough for e-book or e-paper page turn rates, where you can typically turn like 1 page per second. Okay, though it is still short of the true video rate. So here you can compare the two cholesteric drive schemes directly. Okay, so in the conventional scheme you use simply 2 voltage level waveform per line, but each line needs the material's full multi 10 millisecond response, and this was usable only for low information content displays. However, in the case of dynamic scheme, we have seen that it splits the waveform into preparation, selection and evolution, and pipelining the 2 long phases across many lines. Okay, in that case only a brief selection phase is basically sequenced. Resulting frame time that you have seen is the total frame time is delta Tp plus n into delta Ts, this will be small s, okay, plus, or in subscript like this, plus delta Tp. So this is dominated by the number of rows times the short selection interval, and it is not decided by this long preparation time or the evolution interval. So this is the same general principle that was used for every fast bistable liquid crystal driving scheme, that you identify the phase that actually carries the state selecting information and you can pipeline everything else. Okay. So here you can notice the general principle since it has basically appeared now in 3 different contexts in this module, then also in the BTN's 2-phase and 3-phase schemes, and also in the cholesteric dynamic scheme, right, that pipeline the part of the waveform that do not themselves carry state selecting information and keep only the essential brief state determining phase sequenced per line. Okay. So now let us look into the applications of bistable cholesteric displays. So the physics developed over the lecture to real world categories will be helping us to see why the specific combination of this kind of properties like zero field memory, reflective operation, grayscale, then around 1 Hertz update, okay, all these things makes bistable cholesteric technology a genuinely good fit for certain applications rather than strictly inferior compared to the active matrix LCDs, right. So keep the framing general and it will be comparative rather than simply naming some of the specific commercial product, since exact market examples can change over time. Okay, so here you can see that the main features like the zero field image retention and reflective, not the backlit operation, that basically make this bistable cholesteric displays attractive for very low average power consumption. So here the displays only draws power while its content is changing. So it is naturally fit for electronic shelf levels, e-reader style text or image panels, and other applications where contents updates not so frequently. Okay. So wide viewing angle and the paper like reflective appearance, which you get especially from the polymer stabilized black white variant, they support outdoor and bright ambient light readability, where the backlit displays basically struggle. So that opens up a market area for this kind of displays. The dynamic drive schemes 1 page per second update rate is well matched to this kind of applications like e-books and e-papers, okay, even though it falls short of the video rates. So with that, we can basically give a summary of the modules starting from lecture 32, what you have seen. So in lecture 32, we discussed about bistable ferroelectric LCDs, okay, SSFLC, where we talked about two planar schematic Sikdar states which were switched by DC pulse polarity via a voltage time area law. In the next lecture, lecture 33, we have discussed about the bistable pneumatic LCDs, where we discussed about BTN's hydrodynamic 2 pi bistability plus zenithal and azimuthal surface stabilized alternatives, all with their own driving scheme. In lecture 34 and 35, we discussed about bistable cholesteric reflective displays, where we talked about the helical texture bistability, multi-domain grayscale, and the conventional dynamic and the dynamic drive schemes. So what you see here is that the common thread across all the three families is that the bistability solves the passive matrix multiplexing problem, but every material still needs its own carefully engineered crosstalk free drive scheme to become usable. Okay, so you have to carefully design the drive scheme for each of this family to make them a useful product or a useful display. So with that, we conclude this lecture. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.